So we were analyzing the beams, and then this is our strong form. Then we said this is our weak form which we developed last time, where we showed that this is dv by dx. Sorry. Yes, and I think I made a small mistake. Let me undo it. So let me just made a mistake. So yeah, so we know this quantity is equals to m, and this quantity is equals to capital V, which is the shear force and the bending moment. And this comes through these are the point loads of the things, and this is the distributed load. These are the point loads, point generalized forces. That means it can be forces that can be it is either point loads or point moments. And then this is our kind of internal resistance. So this is the total weak form, and we showed that when we are using approximation, that is, instead of y, I approximate y as y tilde plus some error, then this is a capital O, not 0. So where y tilde can be written as di ni summation I is equals to 1 to n, whereas the n is the number of so for two noded elements, let's say let's put it as 2n, because for its where n is the number of nodes per element. We generally solved it for the two noded element, that is, this is node 1, this is node 2. So the degree of freedom would be correspondingly 1, 2, and 3 and 4, which are nothing but our d1y theta 1, d2, and theta 2. That is what our 4 degrees of freedom, which we sometimes I would have called it as di theta I dj theta j. Yeah, synonymously, I would also use d1 theta 1 d2 theta 2, or I would have used it alternatively as capital D1, capital D2, capital D3, capital D4 are the things, and the corresponding shape functions have also been obtained previously. So this is by assuming such a numerical approximation, and then we put it back on the weak form. We also showed that before that we should also use the same interpolation technique for the so using that, what we showed that using the same shape functions, we can write the same equation as integral 0 to, or we have shown this as, let me just use the same notation instead of confusing. I use this one as d1 dash. So this can be written as n times d dash, or d dash transpose n transpose, whereas this one can be written as n into d. So with this, what we did was we came back and we showed that when there is exist a pi, then you can show this weak form can be written as so this is coming from the point loads. This is coming from the distributed loads, and sorry, I also missed one more term. This is capital D. So then we told that this guy can be written as k times of D with D dash transpose minus F naught minus Fd is equals to pi. And we are looking for a choice of d dash where this potential takes the minimum value so that we can achieve the equilibrium condition. So what we did was d pi by d d dash equals to 0. Then we'll get that k implies which we simply call it as k times d is equals to f, where one can show that the k either obtained through this method or from the previous lectures where we used a physical interpretation for estimating the k, where we showed that k for a two-noded element is given by This is the K matrix. And today what we will do is, today we will see how to estimate the load vector. The load vector is given by F, which is nothing but coming from the point loads and coming from the distributed load. Okay, so the easiest way to estimate F of D distributed load is N transpose. So for example, if you have a beam, let's say X is measured from this direction, you have kind of a triangular loading with this as W naught. Then your W of X is equals to W naught L into X, where L is the length of the beam, and at any given X, this is the intensity. So, and we already know our shape functions. Our shape functions N1 of X earlier, which we have derived. If you remember a little bit in a previous class, we have shown that our shape functions are given by one by L cube to X cube minus 3x square L plus L cube, and 2 of X is equals to 1 by L square into X cube minus 2L X square plus X L square and 3 of X plus 3x square L and n4 of X is equals to 1 by L square into X cube minus Lx square. So if I have to find out Fd, for example, for such a kind of a loading, then what I will do is F of D is equals to integral of n1 Wx dx n2 Wx dx n3 Wx dx and 4 Wx dx, which is equals to, I will only do it for a couple of cases, 0 to L so which would be 1 by L cube 2x cube minus 3x square L plus L cube into W naught x by L dx. Similarly, you can define whatever is there. I'm just doing it for the first one, so let me do Fd. The first one would be 1 W naught L cube integral 2x4 minus 3x cube L plus L cube x dx 0 to L. Accordingly, you can do your other integrations. I'm just showing it for the first case, which would be W naught L cube x to the power of 4 by 2 minus x cube L plus L cube x square by 2, 0 to L. You can, using the n1 and 2, you can just keep doing the other stuff. So which would be, when you substitute 0 anyway, everything would turn out to 0. So this would be like W naught L into 1 over 2 minus 1 plus so in this case it turns out to be 0. Similarly, you can do the second one. Uh, so anyway, this turned out to be 0. I took the wrong, so let's even do it for the second one. So the second case, it would be 1 over L square 0 to L minus 2x cube plus 3x square W naught x by L dx minus 2x cube 2x4 plus 3x cube L dx. So that would make this one as W naught by L square this would be minus x4 by 2 plus x cube by L 0 to L. So if I evaluate that, I would get W naught L square into minus half plus 1. Similarly, you can do for the other two. So this will give you W naught L square by 2. Similarly, you can do such things. So if you do things, you can evaluate in this manner. When if it is W of x is a function of some x variable, and let's say there is another case you can also easily determine is the second case, case 2, when W of x is equals to just W naught, that is the beam, whatever is the beam from A to B, it is only W naught which is not changing. So then let us take a fixed beam. If you take a fixed beam and you try to solve for W naught. This I'm not trying to solve it here. Well, if you want to solve it, you can do it. But for the sake of quickly, I will try to invoke the solution which we have already derived somewhere in our strength of materials. We know that reaction forces, because of this, the reactions at end A and B are, let's say this is end A and this is end B, the reaction forces would be something like this, would be WL square, WL by 2, WL by 2, and the moment at each the end will be W L square by 12 and W L square by 12. So if I use this thing, then so these are the reaction forces. So what I call it as, if you have this kind of a loading, if you have this kind of uniform loaded W naught on a node defined by I and j, the consistent loading would be the inverse of this reaction forces. That is, it is equal to put a load of WL by 2, WL by 2, which is opposite to just this reaction forces which I solved from this problem, and it is, this is equal to WL square by 12 and WL square by 12. So now, if you remember, we have taken our kind of convention from the previous class. Let me show the convention from the previous class. This is a positive convention we have taken, that the sagging moments are positive and the hogging moments are negative. That means this one is the positive shear force as it is. This one is minus m with respect to thing, because this is the positive sign, and if you have that one, it is the negative thing. Similarly, and so forth. So I will just invoke the same sign convention at this place. Today, so using the same sign convention, what I can write is, this is, anyway, I'm repeating it for the sake of clarity, WL by 2, and this one was the reverse of the thing, so this is so that means I can clearly write my FP, which is the consistent forces that would be why it is. I will come to the reason that why it is a consisting forces. Now I can write it, this one, as W EL by 2, and this one is a positive thing, so I would write it as W L square by 12, and this is in the positive thing, so, and both the things are giving me in the uh, sagging direction. So this is my consistent loading. If I come to uh, so, so let's see the convention. So these things are kind of sagging moments are positive. So both the side I have a sagging moment. So I had to put it in that manner, and the forces are in this thing which I've taken to be the positive for both the cases. So that is with respect to shear force, but these both the direction the loads are in the thing as it is. So I will have this thing as my consistent loading. Why it is called consistent loading is, if you assume a beam and apply the same amount, a fixed beam, and apply the same amount of um, uh, these kind of loading onto the thing, the amount of reaction forces you get out of this is, oh, I think I've drawn it reversely, so let me just erase it. uh, so this is the consistent loading, so this is the actual thing I have to so this is our consistent loading. So so this is in the minus WL by 2 minus WL by 2, because it is in the opposite direction, and these two are in the in the sagging moment, so these two are in the positive things. So sorry about that. So anyway, the reaction forces for this kind of thing, the the reaction forces for this loading, what you get is nothing but WL by 2, WL by 2, and the directions of this is revert, that is WL square by 12 and WL square by 12. If you look at this reaction forces, if you look at this reactions, because of this is, let's say, loading 2 of loading 2, and if I look at the reaction forces because of the loading 1, let's say this is loading 1, what I got is, these are the reaction forces due to loading 1. So the reaction forces due to the loading 1 is same as the reaction forces due to the loading 2, because if you compare this reactions and this reactions, they are same. Hence we call that whenever you have a distributed load of uniform intensity, then you take consistent loading. So you replace, that means that means whenever you find thing with W naught A and B, two nodes, you replace it is consistent with respect to applying a load of WL by 2 WL by 2 and WL square by 12 WL square by 12, because these two are giving same reaction forces. So for this one and this one, the reactions are same. The reactions would be so these two are consistent. So whenever you see this kind of a loading, I will directly apply, assuming that it is this type of loading, because the reaction forces they give for both the cases are same, and hence for such kind of a loading, my FD distributed load can be taken as per the convention, minus WL by 2 WL square by 12 minus WL by 2 and WL square by 12. So these are the things which we sometimes, a lot of commercial finite element also use such kind of consistent loading. So you can go ahead and derive the things and you will get pretty much similar kind of a thing, or even you get some kind of whatever is, I mean, you go ahead and derive it, you'll get some equation, or you put these things. Since the reaction forces for both the things are equivalent, one can directly replace FD because of the constant loading, which is nothing but the shape functions times of W naught dx. Instead of evaluating this, where W naught is uh, is W, let me call it as W itself, where W is constant, then you can just write it in this manner. So this is called consistent loading, which will be used. So this is one type of generally that is used. And the second thing, let us use the second one. The second one is how to deal with the point loads. Okay, how to deal with the point loads. So let us take a case where this is node A and this is node B, and let us say you have a point load P acting on it at a distance of A when the length of the beam, or when the length of the beam element is L. So then in such cases we will try to invoke something called as Dirac delta function. Let me define what is a Dirac delta function. So the Dirac delta function can be defined as delta x minus xi is equals to infinity if x is equals to xi and 0 otherwise, such that can I talk to you later? They can yes. Can you wait for five minutes? just give me a minute. Okay. I need to relocate from my place because the lab where they are doing, they have to start a compressor. So let me finish this and then we will take a small 5 minutes break, and um, I will try to rearrange my computer at a new location. So let me finish this thing where we are in between. So anyway, let's define such that the direct delta function is such that it is minus infinity to plus infinity delta x minus xi dx is equals to 1. Pictorially, that can be represented as something like this. If I plot my direct delta function as plot, then I have it, it peaks at xi, which is infinity, and this is very small epsilon. And however small it is as epsilon tends to 0, provided the area under this thing is equals to 1. So that is what is your direct delta function. And the other properties of direct delta functions is integral of f of x delta x minus xi minus infinity to plus infinity, wherever wholly if you integrate it, that is equals to function f of xi. So these are the properties, we'll make use of it, and using this we will try to derive the point load. But at this point of time I need to just take 5 minutes break, so that I need to relocate my position, and I'll get back to you in a couple of minutes. Something called as a direct delta function, and our w of x for a point load can be determined as a p load applied at x minus a in the above case. Okay, so when I integrate over uh, w of x dx, I would get minus infinity to infinity, or you can write 0 to L in this case, would be integral of p delta x minus a dx, which is 0 to L in this case, would be equal to capital P, which is what we are looking for the current case. So we are looking for a point load P at a location x minus a. So we can use this thing to handle our point loads, or we can come up in the same manner as we have used in the previous boundary terms. But anyway, let's use this thing. So integral of wx and transpose dx was our boundary term due to the distributed load. So in this case, I would write it as integral p delta x minus a and transpose dx 0 to L. That would give us, if I integrate everything, it is p times of n1 evaluated at x is equals to xa, p times of n2, let me write it cleanly, p times of n2, p times of n3, p times of n4, all evaluated at x is equals to a. So this is what would be our would be the load vector because of the point load. Okay, this is the simplest thing. Now this next case, case 3 would be, what is the thing if you have a point movement at a location at a distance a from the end of the beam. So for this, what we will do is we will replace this. We'll replace this, and we brought an equivalence by saying that it is applied as 2 point loads, which is of P at a distance of B from one another, and such that the first load is at a distance of A. Okay, so what we would do is we make such an arbitration that M is equals to P times B. Okay, this is the magnitude of the thing. Then what we need to do is, we know that the solution from the 1 point load, we also know the solution from the another point load. For the first point load, I can write my F vector due to M at A is equals to F at location A is equals to F due to the point load P at A plus F due to a point load minus P at A plus B. Okay, so now let us write this thing in expansion. We know this solution. This is equals to P times N1, P times N2, P times N3 times N4 evaluated at x is equals to A plus P times N1, P times N2, P times N3 minus P. So at x is equals to A plus B. So at this point, what I will try to do is, I will try to show that in a simplified form we can write P times N transpose evaluated at x is equals to A minus P transpose P into N transpose x is equals to A plus B. Now I want to write this fellow. I will focus on this. Let me take N transpose x is equals to A plus B, and I will try to use a Taylor series expansion such that a Taylor series expansion. So if I want to do this one, let us use f of x plus h is equals to f of x plus f dash x into h by 1 factorial plus other higher order terms are there, which I will just remain it as error or O error function, which converges as h square in this case. So we can say that we can approximate f of x plus h as f of x plus f dash x into h by 1 factorial. Okay, so if this is the approximation using the same thing, I want to expand this a vector n such that about a. So that is n expanded about a plus b is equals to n expanded at a plus dn by dx and transpose into b by 1 factorial is my approximation, is my linear approximation. Okay, so then I take this and put it back in the previous expression where f at MA is equals to f at PA PB, which is nothing but P times of NA plus minus P times of N transpose A plus B. Now I know this thing from this expression and put it back here, then I can write it as P into N transpose A minus of P into N transpose of A plus dN transpose of dx into B evaluated at A. So then this guy gets cancelled. So then I can write this guy as P into B times d n transpose by dx evaluated at A. This is evaluated at A. But what is P times B? I have equated P times B is nothing but M. So this is equals to M times d n transpose dx evaluated at A. So this clearly says that this is because of a movement applied at A. So if you look at its equivalence with respect to point load, before F at P, F of point load was simply given by N transpose evaluated at X is equals to A. So this is for the thing. So this is what we got for the case 3. This is the case 3. So now we are ready to deal with a point load even if it appears in between, I mean point load or a point movement that appears somewhere in between the element. Okay, this is what we have learnt. Okay, and this will help us to kind of deal with any kind of a problem, 1D problem for the beams. Either your point loads can be matching with the nodes or your point loads need not be matching with the loads. In that cases, what you will do is you will simply use this Fm at A or Fp at A and you try to evaluate based on the shape functions at that given point. So for movement, it is the differentiation of the shape functions times the moment. For the vertical transverse loads, it is the shear force is the point load multiplied by the shape functions evaluated at that given place. So in this manner, now we are able to calculate our point loads that are appearing in between the sections, distributed loads, or the point loads that are matching with the endpoints, or so forth. So with this, our how to with the knowledge of what is the shape function for a two-noded element, and what is the load vector for the point load and distributed. Now we are in a position to solve few problems. Okay, so what we'll do in today's class, we'll try to solve a couple of example problems, and let's understand how this beam section is solved. And then in the subsequent class, which will be tomorrow, I'll be dealing with a problem in which how you can try to solve a beam when it is inclined to the horizontal, which is, now we are always solving a beam which is in the horizontal position, but there can also be which can be in the inclined position, uh, something like that. So what we'll do is we will try to know how to deal with such kind of things in tomorrow's class. Let's not jump over our own class schedule. So tomorrow, which when we are meeting morning at around 10:50, we'll try to deal with it. For today, let's try to work out few examples. Once we work out few examples, then we will be in a better position to solve some little bit complicated problems in the subsequences. So for that, let me choose a couple of problems from uh, the standard problem set, and let us solve this problem of first problem. Example, in the problem 1, what we'll do is we'll take a fixed and a pin, and we'll try to put a point load of 1,000 pounds at one point, and also 1,000 pound per foot, or the pound foot at a location, let's say L, and let's say this is at a location A from the end of the beam. Okay, so now let's assume the length of the beam as 2L and A is equals to L. Okay, in that case, how would you try to solve it using FEM, using 1D formulation that we have so far done? The first way I would like to try to solve this problem is by simply assuming that my discretization is such that it is node 1, node 2, and node 3. This is global node numbering. So, and similarly, this is element 1 and this is element 2. Okay, now I know that now my point load is acting on the node something like this. So I can remove it and I can make this problem as, anyway, these two is the continuous node, but I have just simply shown it as separately because this is element 1 and this is element 2, and the point loads acting because I can either show it on this element or completely on that element, because anyway it's the same node. I'm appearing here and there, but you cannot put it twice because that assumes that we are loading it twice, which is not true. So now if it is a two-noded element, the degrees of freedom for this one is d1, theta 1, d2, and theta 2. Similarly, here it is d2, theta 2, d3, theta 3. So there are 6 degrees of freedom, so which I will call it as d1, d2, d3, d4, d5, d6. Now if you have clearly observed, my choice of nodes and elements are such that I want to make this problem as simple as possible. Okay, so that's the reason I choose to model it using 2 elements. I can as well as choose it using one element, but in that case I need to come up with a point load existing in between the element that will have different kind of formulation. So that's the reason I've solved it in this method. Anyway, at later point of time, if the time permits today, we will also show or try to solve the same problem using the other method as well, and then we can show that it is irrelevant how do you model it, you will get a similar solution. Okay. So anyway, for the element 1, the stiffness matrix is given by the length of the element. This element is A, which is equals to L, and the length of this element is also L in our case. So we are fortunate, and let us say its properties, flexural rigidity is EI. So then for the element 1, the K for the element 1 is given by EI by L cube 12 6L minus 12 6L 4L square minus 6L 2L square 12 minus 6L 4L square. Similarly, for the element 2, it's also of a length same as, and the rigidity is same as the element 1, so it will be same as EL by L cube, the 12 6L minus 12 6L 4L square minus 6L 2L square 12 minus 6L 4L square. This is symmetry, and forgot to show that this is also symmetric. Now I need to assemble my global stiffness matrix. Anyway, here we need to show that the stiffness here is with respect to D1, D2, D3, D4, D1, D2, D3, D4, whereas this is with respect to D3, D4, D5, D6. This is D3, D4, D5, and D6. Now, if I want to assemble the thing, the global stiffness matrix, I have to write K global is equals to, let me write with respect to D1, D2, D3, D4, D5, D6, D1, D2, D3, D4, D5, and D6. Now let us see what are the contributions corresponding. From the element 1, so I have coming from D1 and D1, which should be, let's substitute coming from the element 1, so which would be so let me write it out here. This one D1 D1, this one is 12 with, I'll take EI by L cube common, so I'll write EI by L cube common. So this is 12, this is 6, 6L minus 12, 6L, this is 4L square minus 6L, 2L square, 12 minus 6L, and 4L square, which because it is symmetric, I also have to write this as 6L, and this is minus 12, this is plus 6L, and this is minus 6L 2L square, and this one is minus 6L. Now this is the contribution coming from the element 1. Now let us see the element, the contribution coming from the element 2. So for the contribution coming from the element 2, so I know that the contribution coming from the element 2 is D3, D3 is 12. So D3, D3 is plus 12 plus 6L minus 12 plus 6L plus 6L plus, so anyway, that's D4, D4, D3, D4. So anyway, sorry about that. There was a small mistake. So D3 starts from here. So I should have been writing it from here. So plus 12 minus 12 plus 6L, and this is plus 6L minus 6L 2L square, and this one is minus 12. This is plus 6L, and this one is minus 6L. This is 12. This is minus 6L. This would be like 2L square minus 6L, and this one would be 4L square. So what I did was I matched D3 D3 here, because this is D3 D3 coming from the second element. Next, D3 D4 coming from 6L is here. D3 D5 is coming from minus 12 under this. D3 D6 is 6L. Similarly, D4 D3, which would be, I mean, because of symmetry, it is same as 6L here, which is writing 6L. Then this is 4L square that comes here. Then minus 6L will come here. 2L square will come here. Similarly, because symmetry, this is minus 12, which will go here. Minus 6L will be because of symmetry here. 12 goes here. Minus 6L is here. Again, by symmetry, this is 6L. This is here. Then 2L square, which would be here, minus 6L, which will be here, and 4L square, which is here, which will all come and sit here. So then I can simplify it now. Because this is not required, I will delete it. So let me get back. So now if I try to simplify it, I can write this fellow as, this is 24, this is 0. So let me erase it and rewrite it at the same place, or let me just copy it and simplify it at the subsequent step. So this is 12, this is 6L, this is minus 10, this is all are fine. Here this gets simplified, this will become 24, 12 plus 12, 24. This minus 6L plus L becomes 0. And this minus 6L plus L again becomes 0. This 4L square becomes 8L square. And the remaining things are 0, because there are no entries. So these are all equals to 0. So this is my stiffness matrix. This is anyway this d1, d2, d3 which are written is only for our guidance, so that where we are making our entries. So I'm removing the guided columns and things just to show that this is my entire stiffness matrix. This is my K global matrix, and then my D global which is nothing but which is D1, D2, D3, D4, D5 and D6. And similarly my F global is nothing but F1, F2, F3, F4, F5 and F6. Anyway, we will try to solve what is our F's also at a later point of time, but D global can be, we can write it simply right now. The D globals are nothing but D1, theta 1, D2, theta 2, D3, theta 3. Okay, so now we know this. Now what we need to know is we need to know these values also. Let us try to get the forces F on element 1. The F on element 1 is nothing but F1, F2, F3, F4, or simply you can write it as F1, V1, M1, V2, M2, which we have seen in previous cases. So again we need to just make sure our sign conventions are right. So let me just invoke the previous notation to just see that the sign notations are kind of consistently maintained. So the sign notations what we have taken was 2. This is the shear force at V1, this is the bending moment at the thing. So based on our convention what we have used earlier, this is minus m1, because m1 will be going in the kind of a counterclockwise direction, whereas because of the sagging moments it has to be the thing, and this is minus v2 and m2. So these are our forces at the thing. Similarly for the element 2, these are the shear force at element 2, bending moment at element 2, and v3 and m3. This is from the element 2. So before writing it, let me bring that element which I have used. So I'll bring those things here. So I discretize them as this manner. So I'll bring this to this place. So if I look at it, I see that for me, this guy, there are no vertical loads at this place, so it is 0, and there is no moment, this is also 0, and the shear force at this thing is 1000, and this moment is 1000. Similarly, if I look at this thing, everything is 0. So my F global is because of F at element 1 and F of element 2 union of it. So that means I can write this one as, let me write these things as anyway zeros coming from the element 2. The element 2's are whereas coming from the element 1, the forces, point loads, whatever we have seen, would be something like this. There is nothing in the vertical direction, this is 0. There is no moment, this is 0. This is in the reverse direction, sorry I missed it earlier with the minus sign. The moment is also with 1000. So this is in the positive direction sense, so it is also thing. So this is the thing. This is the force vector for the element 1 and force vector for the element 2. So now when we combine it, we have to do it in such a manner that it is with respect to d1, d2, d3, d4, d5 and d6. Coming from the element 1, we had this thing as 0, 0, 0, minus 1000, plus 1000. And coming from the second one, it is plus 0, plus 0, 0 and 0. And hence our F global can be taken as 0, 0, minus 1000, plus 1000, 0, 0. Now, to solve this problem, we have kg, dg, and we have also fg is there. All the things are there to solve this system of equations. But you need to see that since we haven't used any kinematic boundary condition, this kg is singular matrix. This singular matrix is not invertible, so I cannot get dg completely as it is right now. So to do that, first I need to impose my kinematic boundary condition. So let us look at the original thing and let us grab our kinematic boundary conditions. The kinematic boundary conditions for the beam which we are solving today is, let us get the problem. This is the problem. So here y is equals to 0 and dy by dx is equals to 0 at x is equals to 0 and y at L is also equals to 0. These are the boundary conditions. So y of 0 is equals to 0, y of L equals to 0, and dy by dx at 0 is equals to 0. These are the boundary conditions which we have to set. But we know that this thing has been discretized into, so this is d1, d2, d3, d4, d5, d6. d5 is nothing but d3. This is node 3, node 2, node 1. So, and this is nothing but displacement at node 1 and theta at node 1. So, but this is nothing but our d1, and this is nothing but our, sorry, theta 1, and this is nothing but our d3. Or also these guys are nothing but your capital D1, this is your capital D2, and this one is capital D5. These things are 0. So knowing this information, we can write dg as two things: d unknowns and d knowns. So which would be d3 is not known, d4 is not known, and d6 is not known. This is d unknowns, and what we know is we know d1, we know d2, and we know d5. So that is our d unknowns are d3, d4, d5, and our d knowns is d1, d2, and d5, and in our case they all turned out to be 0. So I can write this thing as du and a 0 vector, which is 3 cross 1. So now I can break my kg into dg g as k uu k uk k ku and k kk. D unknowns, D knowns, correspondingly this would be F for U and F for the K. So now let us look this thing. Since this dk is a 0 vector for 3 cross 1, fortunately this into this is 0, this into this is 0. I can write in this case as, only in this case, k uu du is equals to fu, and similarly k ku du is Fk. Now let us use the equation 1, and when you are using equation 1, what we will do is our D unknowns is nothing but K UU inverse times Fu, and once you know this, you take this and substitute in the equation 2, you get F which is nothing but reaction forces at the supports, because where you have constrained it, there you will develop a reaction forces. So FKs are nothing but your reaction forces. It's nothing but KU times DG, or you can also write it as, I mean, this is unnecessarily way of writing it, because you have, by this time you already determined DUs. Sorry, this is U. So this is KUU inverse of FU. So in our case, let us find what is KUU. So to find KUU, I will go back here. I will rewrite these things again, which is nothing but D1, D2, D3, D4, D3, D4, D6, and D5. Similarly, D1, D2, D5, and D3, D4, D6. Now I'll try to strike off all the things that is which are known. So these things are known, so I will strike off D1, D2, D5 column, and similarly I will also strike off my corresponding rows, D1, D2, and things. So my KUU is the remaining elements, which is nothing but, if I compare it from here, so my KUU is equals to, let me just copy it from here for simplicity. So KUU is nothing but 24 is equals to EI by L cube 24 0 6L 0 8L square, and this is 2L square, and this one is 6L, this is 2L square, and this one is 4L square. So, and similarly my KU can be obtained by, now KKU is like the rows are these are still intact, which is like knowns, which is this things are still intact. Anyway, I'll redo it for the purposes. I could have, okay, I'll just explain it since we are running out of time. So I can quickly write it as these things are still, rows are still knowns, but the things that are eliminated are these things. So that means these ones are the kind of KU. So that is minus 12, 6L, 0, minus 12, 6L, 0. Just see only through which your horizontal line is passing, and there is no vertical line. That is minus 12, 6L, 0, minus 6L, 2L square, 0, and minus 12, minus 6L, and minus 6L. Now, since we have this thing at our thing, I'll remove this. So this is our so this is our KKU, KUU and KUK. So our DU is equals to, this is done. Now we have to do DU, as we already declared. It is nothing but D3, D4, D6 are also nothing but our D2, theta 2, and theta 3. Similarly, now we need to get FU from the FG, which is nothing but you'll go and strike off all the things that are corresponding to this one. So that means similarly your F1 will be gone, F2 will be gone, F5 will be gone. You end up with F3, F4, and F6, which is nothing but, here in the last thing we got this one as 10,000. Let us see, but I think it is plus 10,000. So D3, D4, and this is F3, F4, and F6 is minus 10, minus 1000, minus plus 1000, and so this is minus 1000. This is plus 1000, and F6 is 0. Now we have FU, we have KUU, our DU is equals to KUU inverse times our F. So since we know totally this KUU, we can find out its inverse, and we know this thing we find out, since we know FU, we just multiply with it. After we take this inverse, that will give us our DU, and once this DU is there, we determine our reaction forces Fk as KU times DU, which is obtained from this place. Okay, so this, what I will do, the evaluation of this part of a problem example, I'll do it in the next class, since we are heading out of the time, so which would be tomorrow at 10:30. So we will continue from the same point, and we will finish this problem tomorrow, and we will continue couple of other simpler problems, so that you get habituated how to solve these things, and then we'll go for a beam inclined, a beam which is inclined to the horizontal, so that we can solve two-dimensional frameworks. Okay, so see, this is the green thing. The green thing is coming from the element 1, while the red thing is coming from the element 2. This is K element 2, and this is K element 1. Okay, since for element 1 and element 2, D3, D4 has common, so this will also contribute stiffness at D3, D4, and element 2 also will contribute stiffness at D3, D4. So that's the reason this has been there, but I never put all the elements as 0. The stiffness element is as it is. I don't know what you are referring to. These things are set to 0. These are all zeros because there are no contributions. So maybe if you are confusing with respect to that. So these are set to zeros because they are not been contributed by the element 1 or element 2. Element contribution only comes and sits here. Element 2 contribution comes and sits here, and there are only 2 elements. When I club it, this element 1 is not connected to d5, d6, so it will not contribute. So d1, d5 has 0, and d1, d6 is 0, d2, d5 is 0, d2, d6 is 0. Similarly, a transpose of it is also 0, because if you look at it, the element 1 is connected to only d1, d2, d3, d4. So that means in the global matrix, it will only contribute where a combinations of d1, d2, d1, d3, all these 4 combination. I mean, if you tweak one, some other contributions can be obtained. But since you are not seeing d5, d6 in this element, you cannot get contributions at that place. So I hope I have answered your question. So what we'll do is we'll take up this problem tomorrow. If you still are not understanding the problem, we will see. We will go a little bit slow and try to incorporate uh, the results pretty slowly so that one can understand the problems. Okay, so with this we will end today's lecture, and we'll continue tomorrow at